associate professor of audiology, communication disorders at Rush also. And normally what I do, I have a research lab. And normally what I do, I try to figure out, well, fundamentally, how do we understand things in the world through audio? We close our eyes, we can still hear footsteps, keys, cars, and so on. We can understand speech, and so something must be happening when the pressure changes in the air somehow comes to the ears, and then they're converted to some sort of sensory representation, and then brain makes something of them. And we don't know any of that. We just know that there's somebody walking in the hallway and there's a baby crying and so on. So fundamentally, these are the questions I'm interested in. But practically, the bulk of what I do is try to develop different computer training programs, rehabilitation methods for people with hearing problems, mostly for people with cochlear implants. So cochlear implants are the devices that basically it's a true electric hearing, where you electrically stimulate the auditory nerve, and people go from being completely deaf, some of them, to being able to talk on a cell phone. I won't spend much time talking about this today. I'll come back in February and I can talk more about that part. But another part of what I do is try to figure out how we can communicate better. And so there are different levels of what communication means and what performance means. So I'll briefly touch on some of them. So this particular project has to do with how we can, when we talked with Bob, with Jason, one idea that came through is that how can we take a human being and help him with technology to do things better, right? And I guess that's one of the ideas of the course, Human Admentics. Not just helping people who have problems, but helping people who are doing well, but maybe technology can help them do better. So I'll touch on that also. So what is audio derivation? Well, let me say, we'll go to the next one. So the main idea of this project would be to use a signal processing application to slow down speech. And in situations when speech may be difficult to understand for various reasons. And when speech is difficult to understand, we exert more effort in understanding it. So two people can understand speech at about the same level if you just ask them to repeat the words. But the amount of cognitive effort that they make in order to understand it draws resources from other tasks that they may be doing, such as driving a car, maybe washing dishes is pretty simple, but math problems, whatever it is, helping kids with homework, and so on. So the signal processing application is something that wouldn't need to be designed. There are sort of standard applications that work pretty well, and so that's kind of a solved problem at this point. Well, let me go into how it works first. Now I'll tell more about the background. So here's a sort of garden variety sentence from the IEEE sentence database that was designed to test intelligibility. And if you could play the top one, this is the regular tempo.
A stray cat gave birth to kittens.
Right. So I hope everybody found the sentence easy to understand. Granted, this is not the sentence you might have expected, but this is not a typical sentence. But the sentences in that database were designed so that they would be very logical, consistent, but at the same time not the most usual sentences. So you could really test whether people understand the words. Anyway, so now this being in quiet, this was easy to understand. But let's play.
A stray cat gave birth to kittens.
Right, so this is a digitally modified, time-stretched version of the sentence. And the way it works, this particular one, it basically, if you look at the waveform, there are cycles. So it finds the zero crossings for the cycle and then basically replicates the cycle. What this allows to do, it allows to preserve other qualities of speech the same while only controlling the tempo. So the overall length of the utterance increases, the tempo increases, but you don't have any changes in pitch. Those who have played with turntables, with the cassette players, you know that if you slow things down, the pitch would also change. And so this, for a long time, this was a problem when people, the idea of time stretching is not new. This was put forth maybe in the mid-50s, when people started doing this experimentally. These were people in Bell Labs, mostly at MIT, were trying to design applications for similar purposes. But because the other qualities of speech were suffering so much, this sort of killed the idea at that time.
Sorry.
Was there a previous? Yeah.
No,
we can move on.
I wanted them to hear the sound again.
Okay.
The stray cat gave birth to kittens. The stray cat gave birth to kittens.
So here I'd like to give some examples of situations where we can have communication becomes effortful. In the previous sentence, this was easy. You didn't need time stretching to understand the words. Now, there are some situations that I listed here where people may actually benefit from having speech slow down a little. And one particular situation is when you have a non-native speaker like me, maybe somebody else, with a different kind of accent, speaking with you. Although, granted that non-native speakers tend to speak slowly to begin with, this is not always the case. And then there may be other factors that may be happening. For example, you may be driving. The speaker may be totally unfamiliar to you. You may be listening to this person on the phone. So that's one type of the situation. Let me talk about them, and then we'll go and listen to specific ones. Now, another type of situation, let's say you're going to a foreign country. How many people speak another language somewhere? Okay, most of you, right? So if you go, how many people are really fluent in that language that you speak? Okay, fewer. So let's say you have been studying French, but you're not completely fluent in it. Let's say you go to France and you're trying to find out directions. How often you can ask a question, but you don't really understand what people are saying back to you. It can happen. And also there is sort of a subjective feeling that people speak much faster in the native language that you really like them or expect them. So that's another kind of situation where a slowing down somebody's speech artificially may potentially help. We're calling to make a hotel reservation, another one. Another type of situation, as people get older, generally their recognition declines. Not everything at once, and I don't want to put everything in there. There's a number of things that stay flat for a very long time, but generally the speed of processing and a number of operations may decline. So potentially these are the situations, and you probably heard all this comment, young people speak too fast. So whether or not that's true is another story, but that's potentially another situation where slowing down somebody's speech may help someone. And another one is when people are developing Alzheimer, dementia, also their cognitive ability, right? Speech perception is not just mechanical process where you take sensory input, you put it into some box, and it matches things with words. It's in this very complex device, which is tremendously interconnected, called the brain. And so all the other things, or many other things that are happening, affect how well you can perform the task. So people who have cognitive issues may also benefit from speech coming at them at a slow rate. And finally, I've been mainly focusing on situations where we can have interaction one-on-one and quiet. How many people have problems when they go to a bar, when other people are talking about? What about situations when, sort of air traffic controller, or any type of situation where competing messages of similar form commentary around at the same time. So these are kind of the top ideas that came to my mind. There may be some others, but these are definitely ones that can be tried. Now, so now we can go with some examples. So the non-native speaker example. Now, before...
If you want to go to
Sorry.
Gina's pizza shop, I can tell you the best way to get there.
Try to remember the
Go straight down the
directions.
street and follow the signs for the Johnson Expressway. However, don't actually go onto the Johnson Expressway. When you get to the on-ramp, take left onto Cleveland Street, the main street in town. You'll go past the big school called Cleveland High School. Right between the church was a yellow door and the church was a blue steeple. There is a small alley just past the church was the blue steeple. Take this alley for several blocks and turn left on the third road you come to. Eventually, the road was split into two. Take Fillmore Boulevard, which is the one on the right. A block and a half later, you'll see the sign for Gina's Pizza Shop, also known as the best pizza place in town.
Okay, so if you're in town, you can find Gina's Pizza Shop very easily, right? So just for comparison, right? Now, so this is a naturalistic task. You actually ask somebody for direction. Let's say you call somebody, whether a friend or somebody recommended, you call the shop, and somebody told you the directions. Now, let's try the slower version of it.
If you want to go to Gina's Pizza Shop, I can tell you the best way to get there. Go straight down the street and follow the signs for the Johnson Expressway. However, don't actually go onto the Johnson Expressway. When you get to the on-ramp, take left onto Cleveland Street, the main street in town. You'll go past the big school called Cleveland High School. Right between the church was a yellow door and the church was a blue steeple. There is a small alley just past the church with the blue steeple. Take this alley for several blocks and turn left on the third road you come to. Eventually, the road will split into two. Take Fillmore Boulevard, which is the one on the right. A block and a half later, you'll see the sign for Gina's Pizza Shop, also known as the best pizza place in town.
So I don't know if you would be able to find Gina's Pizza Shop now, but I think maybe your chances will be a little higher. So that's one example. Now let's say anybody speaks French. Okay, so for people who speak French, this one is regular tempo spoken by a native speaker. Maybe you can even understand what the speaker is talking about.
À Paris, c'est vrai qu'il y a des crottes de chiens par terre partout. Bon, c'est une grosse différence aussi.
So I don't know. Maybe we can. Did anybody understand the message?
That's what they sounded like in Paris when I was there.
Well, this guy is from Paris. So let's try the other one and see. So this is right. This is the slower time.
À Paris, c'est vrai qu'il y a des crottes de chiens par terre partout. Bon, c'est une grosse différence aussi.
So for people, I speak a little French, but not enough to understand either of them. But the problem was that in Paris, people didn't clean up after walking with the dogs, when the dogs pooped out. And so I think this is actually different now. The last times I were there, the streets are very clean, so they must have passed the law. But this guy, this was recorded in New York, and he was commenting that in New York the streets are actually clean, and you don't step in the dog poop all the time. So that's the mystery French message. Anybody Japanese? You speak Japanese? Oh, okay, let's try that.
実際に、東京と大阪の言葉の違いではどっちかというと東京の言葉でしょうけれども、
Let's try the other one.
実際に、東京と大阪の言葉の違いではどっちかというと東京の言葉でしょうけれども、
So the point is that you know, if you don't know the language, it's not going to help you. But if you do know a little bit or somewhat know, then even a person, a listener, more time to process the words, to search for meanings, and to put, so you can know the meanings of each individual words, but you need more time than a native speaker to actually put this together into a meaningful sentence, or understand what the person means. So that's another one. And finally, what I'd like to listen to is that here's a situation that this is based on it's called a Coordinated Response Measure Corpus. This was developed by Air Force researchers. It's Wright-Patterson Air Force based. And this simulates sort of the tasks that air traffic controllers or the pilots might do. So they have these messages, you know, this kind of an idealized task. But where do you need to land? And so people are identified by, or specific actors here, identified by particular call signs. So let's say your call sign is Baron. And so there is a particular color number code. And you have to figure out first who Baron talker is among the three. There will be three talkers. And then the Baron talker is going to say, the whole utterance is going to be ready, Baron, go to such and such color and number now. And then there are going to be two other talkers at the same time, and they're going to be identified by other call signs, and they have to go somewhere else. So here's a regular tempo example.
Ready, Baron, go to now.
Right? So one of them was there. Maybe you heard it, maybe not. Right? Maybe you can play it one more time.
Ready, Baron, go to now.
And this is an easier version of the test because they're not all the same sex, and that means that men and women have different pitch of the voices, which helps people actually to separate the voices together. The next one is the situation when you actually have them all to be of the same sex.
Ready, Baron, go to now.
Okay, so this is an example of the task that somebody who is doing traffic control or a pilot who needs to land at a particular place may be dealing with. So now here's a slow tempo example. Let's do that first. Let's do the other one first.
Yeah, no.
Ready, Baron, go to white and green now.
Was that
Ready,
easy?
Baron, go to white and green now.
Okay. So let's do the other one.
Ready, Baron, go to green 4 now. Ready, Baron, go to green 4 now.
So the only difference between the ones on the left and the ones on the right is that the tempo of the Baron talker was slowed down. Right? There is nothing else that changed between the left one and the right one. And everybody would probably hear a little bit of difference. So now, why haven't people done that? People have tried it. As I said, the idea is not new. It was first suggested and tried initially in the 50s, both for time compression, making speech artificially smaller, and for time expansion. At the time, when people did time compression of speech, the way people did it in the 50s, they would just basically break speech in small chunks and throw things out. So if they would just kind of throw every other part of speech, and people usually did it in less than 40 millisecond chunks, so that it would still contain enough information to reconstruct the message. And this was fairly effective for compression. Now, if you try this for time expansion, this becomes a little bit more problematic if you just use this approach. But the technology caught up by the 90s, and you can do this now very simple. You can do this online. It's not an expensive procedure to do. And the other part of it, so people have tried it even recently. What I think stalled the process a little bit, that people approach this from the data-limited perspective. So they're sort of, in psychology, when people talk about information processing, they talk about data-limited processes. and resource-limited processes. So when you hear, let's say, very quiet speech or speech and noise, not all of the speech may be audible to you, right? So you get only fragments of the original waveform, basically delivered to your brain. You have an impoverished sensory representation, and your mind usually fills the gaps in, right? So if you approach this, okay, so if you just have more data of representing the original signal, that should help. And that's how people approach it, and I found that this hasn't really helped all that much if you do that. What has been missing from the picture, and this is some of the work that my colleagues and I have been doing for a few years now, is the other part, the resource-limited process. If you just look at intelligibility, which is traditionally defined as how well somebody can repeat words that you say to this person, without concentrating on comprehension and actually understanding the meaning of the words. If I say the word table, you repeat the word table, right? It doesn't matter whether you know what table actually means. It's whether you can repeat it. So the tack that we're taking here is that if we look at the task that draw on processing resources, on cognitive resources, that's where the benefits of time expansion will really be likely seen. So if we go to the next slide, maybe the following, right? Maybe let's do the next one. Come back to this one. So how do we know it's working? So instead of doing intelligibility tests, maybe what we can do is comprehension testing. So similar to this one, you listen to a passage telling you directions, and you say what the directions are, or you listen to a passage and then you have to answer the questions about the passage. So you actually process the meaning of the passage. You're not just basically repeating the words in the passage. There is a task called the DIAPICS task developed by researchers in the Northwestern University that basically there are two people. They sit in different rooms. They may not see each other. Each one has a picture. And the pictures are similar but have a number of subtle differences. And so they have to talk to each other interactively and figure out all the differences between the pictures without actually seeing each other's picture. So when one person is a non-native speaker and one person is a native speaker, one person has some sort of a memory problem, you see how slowing down speech may or may not help you with this, but that can be a validation of the task. Another one is then you do a comprehension task and you also drive a car, right? We don't actually necessarily want people to drive a car while doing this, but there are driving simulators that you can use to actually have set a course for a person and say the person at the same time is doing a comprehension task, such as having to listen to a passage and answer questions about it. And you can see whether there are benefits in that sense. And so in that I see the real benefits of slowing down speech. Now there are other things more experimental, more sort of theory-minded that we're doing, but I don't necessarily think we should worry about this now. So we go back to the previous slide, how can it work, right? So the simple one, you do a phone app, right? And then everything that comes in, you have an opportunity to slow it down. Another one, you can put it on anything on the computer. If you do anything voice over IP, then Skype, any kind of message, if you have an opportunity to slow things down, you can play with that. And also they're in-the-ear devices, which gets a little bit more complex. So computationally, this is easy to do. You can do it. People have done this on iPhones, so why not do it on the ear device? But the problem is that you have to know who the speaker is, because otherwise you'll be slowing down a whole lot of other things. If you don't know the pitch of the talker, the program starts making errors and copying the wrong cycles when there is noise around, then you may get other problems. But this may be a solvable problem, but it's potentially another way this can apply. So I'll stop at that. Maybe sometime we can, if anybody has questions, we can talk a little bit now and maybe some later.
We have time for a few questions.
Yeah, go ahead.
What do you see our role in this project?
Well, I can, I'm not an engineer, and I know where to find this applications. I know I can tell you there's a free program where you can play with speech with this and do different kinds of extension. I don't know how to put it into iPhone. I don't know how to put it into a computer. And so if somebody knows that, that would be one potential thing. So you can actually do this in real time. In terms of the ways, how do we know it works? You know, we can actually design a way to validate whether or not it's doing something. So if you come up with an app for an iPhone or for a computer, we can actually have a situation where we run a little experiment along any of those lines. So one group may be doing a comprehension and driving task. The other one may be doing, what was there? I don't remember what I put there. But there is another potential, the different types of validation. One group may be focusing on native versus non-native speaker. Another group may be focusing on people with traumatic brain injury who have some sort of working memory problems. So these are some possibilities.
If I may, there's a classic human factors test that you can do. It's a dual task, where you have a main task and you have a secondary task. And so they measure your workload by looking at how well you do the secondary task. And as the workload for the main task goes up and up, the secondary task gets put to the side, and so its performance goes down. So you can do that kind of experimentation where, for example, someone's driving the car. What's your main task? Well, I have to drive the car so I don't hit a pole. And yet you're talking on your cell phone, which is what happens every day. And you're driving along, and as the situation, or if all of a sudden it starts snowing, or there's fog, or there's something else, and the workload to drive at this speed on this highway starts to go up, and the question is talking to Aunt Nanny on the cell phone going to cause you to take resources away from your driving skill, which is going to make your driving worse? And you say, well, that doesn't make any sense. People aren't going to listen to the cell phone. Well, that's not what happens. People text. People do all sorts of wacky things when they're driving because they've been driving for so long they didn't think it's a big deal. And yet they don't understand that their workload is causing them to slough off the important stuff in driving and attend to the secondary task. So there are lots of different experiments that you can do where someone has a main task to do and they have this cell phone task that they're doing, and you can also look at how they're doing with a tertiary task as well.
How do you see this working in real time? I mean, I'm thinking about the in-ear devices when you're talking to someone. If you slow down what they say by 50%, that's well and good for understanding, but suddenly you're 50% behind the rest of the world or behind the conversation.
If you think about the actual time, the average word is about 300 milliseconds. So the sentence is a little over a second. So if you multiply this with, say, 1.5 is too much probably. So 1.3. So if you have it lengthened by a word by 100 milliseconds, 70 milliseconds, I think it may seem like a lot of time, but people adapt. Basically, some people naturally speak slower. And as in communication, we just realize that this person doesn't speak so fast. And when you talk on the phone, you don't even know what is your expectation. How fast. It's kind of maybe a little bit unrelated. But if you look over how fast you browse things on the internet, what seems perfectly acceptable 15 years ago, where you would connect for 5 minutes and then you would click on the site, it would load. At the time, you give an increment of maybe 10 seconds. This is like a huge. This is flying now. Now, if something doesn't load within a second, you click on a different site, on a different link, right? So this is a little relative. So I see your point, but I think people adapt.
It's a particularly valid question, though, in terms of social situations. I mean, if we were listening to you, if one of us was listening to you slow down, well, there's also the visual component, which I'll set aside for a second. It's sort of like watching a film. But I would be hearing, I'd be getting this delay in hearing. So if I wanted to interact with you, how much would this accumulate? And would accumulate to the degree that when questions started coming in, I'd still be hearing you.
Right.
You know, so how do you compensate?
Sure. So, well, two things. First of all, the visual component is not so bad because we have about 250 milliseconds length of the syllable that people don't really notice the discrepancy.
I'm down to try it.
We're kind of built the way that we can compensate for a lot of incongruency, just because we really go for the meaning. And so, you know, just like when you go to a drive-in movie theater, you know that the speaker is on your left ear, that the speaker is in your car radio, but you actually think that it's coming from the screen, right? It's the actor's lips moving. So our systems that have evolved, whether purposefully or not, to actually accommodate this stuff. The other question is that, as I said, that in-the-ear device need a little more work. The specifics may vary, because as I speak to you, I make pauses. And so one potential thing is to have an energy detector that notices silences and compensates it so it actually doesn't build up during my whole, 1 hour speech, but every time there is a little bit of a compensation. So I wouldn't necessarily, I put the in-the-ear part there because I think it is possible if there is sort of a concerted effort to look at these things. But there is a number of problems to solve there. I think the phone app or a basic computer app that works online is, it's there. It's more, the free program that I mentioned is called PRAAT, P-R-A-A-T. Some of you may know, some of you may not know, but it's been developed by two guys in Netherlands, and they made it available for free. You don't need to install it. It can work off your jump drive. It's an extremely good free program. And one of the things that it can do time stretching using Psola, which is the method that I use. And so if you download it and you get some speech and play with it. Now another thing that we've done before, you can actually use PRAAT time stretching application or whatever is the processing. You can call it from C. You can call it from MATLAB, but if you can call it from MATLAB, you can call it from C too. Right? So you don't need to reinvent the wheel. There may be other ways to do that, but this is just like the easiest ones to try. Right? So if you have like maybe something written in C that can work in real time, then you can really in Java, whatever.
I just have a quick question. Can it do it in line, or does it have to render the slowed down tempo? Like, can it do it as someone's talking, actively slow down their speech?
Well, it would have to buffer. I mean, it can. If you build it the way that it takes, whatever. I don't know what actual speed of processing would be, but you can potentially have like 4 millisecond buffer and would do that. It needs to have the speech. It needs to estimate the pitch of the person. So for this kind of simple application, having heavy noise would be a problem, potentially, especially if it's multiple talkers. But it would be enough to see if it's working for this particular task, and then whether it warrants further finer refinements that can be done. Sorry, I've taken.
No, that's okay. Thank you, Joe.
Okay.